Today's final speaker is Chris Skinner of the University of Michigan, and his topic is the modularity of Galois representations.
There we go. I'd like to thank the organizers for asking me to come and talk on this. I'm going to begin by saying something about what this talk is not. This talk is not a real detailed exposition of sort of proofs of modularity of Galois representations, but more of an overview of what's known and sort of this progress that's been made in the last 5 years or so. And so I invite all experts to go, if they feel like they need to walk off the cookies they just ate, they're more than welcome to, and they wouldn't be offending me. So there's the title, Modularity of Galois Representations. And for the most part, I'm going to concentrate on the two-dimensional situation. So two-dimensional Galois representations. And then, if time permits, I'll say a few words at the end. So all talks have to have a beginning. And the beginning of this one is starts with a modular form F, which we'll assume to be the classical holomorphic cuspidal eigenform, level n, some integer n with the integral weight k and a character chi. And just to assume it's an eigenform means that the action of the Hecke operator T sub L for a prime L on F is just some scalar, which here is denoted by C sub L of F times F. And then the connection between such objects and Galois representations came out of the work of Shimura, Eichler, Deligne, Serre, and others. That if we fix a prime P, and then there exists a two-dimensional representation, denoted here rho sub F of P, of the absolute Galois group of Q into GL2 of QP bar, the algebraic closure of p-adics. And this representation has some remarkable properties. Well, first of all, to be reasonable, it should be continuous, say semi-simple. Since we're dealing with cuspidal eigenforms, it turns out to be irreducible image. The determinant is easily described. It's the character chi times the integral power, or some integral power of the cyclotomic character. So epsilon, the rot will denote the p-adic cyclotomic character, which gives the action of the Galois group on the p-power roots of unity. And the power is k minus 1, where k is the weight of the form. This representation is unramified at all primes L, not dividing the level or the prime P. And unramified, of course, means the image of the inertia group under the representation is trivial. And then the truly remarkable property of this representation is that the trace on Frobenius elements picks out these eigenvalues for the action of the Hecke operators. And of course, implicit in all of this is an embedding of the algebraic integers into an algebraic closure of the p-adics, but I'm not going to get into such things. So, and this is true for all primes L not dividing the level or P. Since this is a conference on automorphic forms and automorphic representations and things, we can reformulate this in jazzed up language. And so a sort of a refined version of what was just stated. And here we have to appeal to works of a few other mathematicians, Langlands, Carriol, Wiles, Taylor, and others. That, of course, our eigenform F corresponds essentially to an automorphic representation, pi sub F with holomorphic discrete series at infinity. And so we can sort of think of our rho sub Fp as really a Galois representation attached to this automorphic representation. And this property about the traces of Frobenius being equal to these Hecke eigenvalues can be rewritten essentially as saying that if we restrict this Galois representation to the Weil group, or really the Weil-Deligne group at a finite place, then our representation is the representation that you get from the local Langlands correspondence. It's this rho sub pi f of v. And here, you'll note the only restriction is that v is not equal to p, whereas over here, I wrote it with a restriction on the prime L not dividing n times p. So this is a slightly stronger result and tells us what's happening at places of ramification as well. And so I should say also that the same theorem is known if you replace the field Q with a totally real number field F, and you place F with a Hilbert modular eigenform or a automorphic representation of GL2 of the totally real field F with suitable conditions at infinity. So because of the association of these Galois representations with automorphic forms or modular forms, the L function for the Galois representation is just the L function of the automorphic representation. And since I haven't said anything about how I'm normalizing any of my isomorphisms, I don't have to tell you what this equality really means. But what we should get out of this, or what we do get out of this, is an analytic continuation, because our L function of our analytic object has an analytic continuation. And as well, we get a functional equation, which is pretty much everything you could possibly want for an L function. So a hope might be that all reasonable Galois representations come from modular forms, so that the L functions attached to these Galois representations would have analytic continuations and functional equations. So this leads into something which I'll call, for this talk at least, the modularity conjecture, and I'm ascribing it here to Fontaine and Mazur, just because that's sort of the place I know where it was written down. They indicate that it was floating around sort of in the mathematical folklore for a long time, and certainly, versions of this, like the celebrated conjecture of Shimura and Taniyama on modularity of elliptic curves and the like, is behind all this. So the conjecture would say something like this. Suppose that we have a continuous, semi-simple, irreducible, two-dimensional representation, chaotic representation of our absolute Galois group of Q. And suppose further that this representation is unramified at all but finitely many primes L. So L is always going to denote a prime. And we make a further restriction that our representation be what we say, or what we call, potentially semi-stable at P. So we're making a restriction locally at the prime P, meaning we're imposing some hypotheses on the restriction to the decomposition group at the prime P. And what it means to be potentially semi-stable is a fairly technical definition, but what it means in practice is that it looks like the kind of representation you would get on the Eitan cohomology of some reasonable variety. And then I'm going to go ahead and throw in the condition odd, which may or may not be in the statement by Fontaine and Mazur. And odd means the restriction to complex conjugation has eigenvalues 1 and -1. The representation on a complex conjugation. And then under these hypotheses, one would conjecture that our representation comes from a modular form, at least up to a twist by this cyclotomic character, so up to some Tate twist of a modular form. So in particular, it's isomorphic to one of these rho f p's for some modular eigenform f. And you can make a similar conjecture with Q replaced by a totally real field. I should say at this point a few words about these conditions and how necessary they are. I mean, certainly you have to have these conditions if you're going to be modular, because those were the sorts of conditions that modular representations, or representations attached to modular forms have. You might ask, can we weaken these to some extent and still recover them? For example, do we have to impose that our representation be unramified at all but finitely many primes L, or do we get that for free? And it turns out that these kinds of conditions are pretty much all necessary to impose, so that you can in fact find Galois representations that are potentially semi-stable at P, continuous, semi-simple, irreducible, but ramified at infinitely many primes. And in fact, Ravi Ramakrishna, I believe, has constructed such things. That'll come up more. Why odd? That's because the ones I didn't say put that condition on the modular forms, but it comes from the conditions on and the Galois representations attached to modular forms are odd. So I'm going to pose that condition on here. Holomorphic modular forms are odd. It's a big question where the even ones might come from, and there are those that would hope that they come from Moss forms. I hope they come from Moss forms too, but I just have any reason to believe it. So to say what's known about this conjecture, or even to talk about results in the direction of this conjecture, I need to introduce something called the residual representation, or the residual representations attached to a p-adic Galois representation. So we start off with some continuous representation of the absolute Galois group of Q. And then it turns out one can show that this, in fact, while we're talking about it as taking values in GL2 of QP bar, which is something very big, really there exists the ring of integers of some finite extension of QB such that after possibly changing our basis of our representation, we can realize it as taking values in GL2 of this ring of integers. So it's a pretty nice thing. So we can really restrict attention to finite extensions of p-adics. And of course, once we have it into GL2 of some discrete valuation ring, we can reduce mod a uniformizer. So you can fix lambda, say, to be a uniformizer of this ring O, and look at the reduction of the representation mod lambda. But we've made some choices, and to get independent of most of these choices, we have to take the semi-simplification of this representation. So, and say the semi-simplification as we realize it, say, into the algebraic closure of this finite field. You only have to worry about the algebraic closure perhaps in if you're dealing with characteristic 2. And this brings me to a second kind of modularity conjecture, which I'll call the mod P modularity conjecture, which really should be called Serre's conjectures, or usually is called Serre's conjecture. So we start off with a finite field of characteristic P now, and we look at continuous, irreducible, odd representations into GL2 of this finite field. And then there are sort of two conjectures, one weaker than the other. They're all sort of built, really, the second conjecture subsumes the first, but I want to separate them for the purposes of this talk. And the first you would just conjecture that this representation is the residual representation of a representation attached to a modular form. In other words, this rho 0 that we started out with is isomorphic to the residual representation of rho fp for some modular form f. And, well, to make this into a good conjecture, at least one that you can sort of try to verify computationally, you might want to pin down where this f arises, say what level, what weight, what character. So we have a finite dimensional space in which to check. And Serre does exactly that. He prescribes a weight, level, and character depending, and with an explicit recipe coming from the representation rho 0. And then what we have, the most general result that we have in the direction of this kind of mod P modularity conjecture is the epsilon theorem of Ribbit and Diamond and many other mathematicians, that if P is an odd prime at least, then conjecture A implies conjecture B. That if we know that the representation comes from some modular form, it's the residual representation of some modular form, then it actually is the residual representation of the right weight, level, and character. And this is critical in many of the proofs in the direction of the characteristic zero modularity conjecture. Oh, another comment I want to make is sort of implicit in this, of course, is that there's a characteristic zero lift of our representation rho zero, that there's some representation of the Galois group of Q bar over Q into GL2 of some ring of integers of a finite extension of QP. And so you might make an even weaker conjecture that such a thing exists. And proving that seems to be very difficult. And once again, I sort of mention some work of Ravi Ramakrishna, who has shown in a number of cases that you can do this. And that too will appear in some later work that I mentioned. All right. So moving on. So what's known about this modularity conjecture? Maybe I'll put this conjecture up here so we can have it to refer to. Well, so early results would be things like, well, CM elliptic curves are modular. So this goes way back. Well, way back to early part of the 20th century. Well, more generally, you can prove some results about CM representations. So by CM, I mean things with complex multiplication, of course. And then if you want to prove that a specific representation is modular, if someone hands you a representation and asks you to prove that it's modular, say they give you an elliptic curve, then theoretically, you only need to do a finite amount of checking. And this sort of goes under the heading of the faulting Serre method, which is sort of a refinement of this idea that you only need to check that you have an eigenform and you have another Galois representation and their eigenvalues agree up to a large number of primes. But other than that, there were only spotty results. And so in the early 90s, of course, we had a breakthrough. Well, maybe I'll leave this up here so I can make some comparisons. Put this up here. So we had this theorem, which I due to Wiles, and that if P is an odd prime, and we have one of these representations that we're interested in, a two-dimensional p-adic Galois representation, and we want to assume, well, that it's continuous and irreducible, unramified away from finitely many primes, that it's odd. And here we'll be a little more specific than just being potentially semi-stable at P. We're going to say we're flat, meaning we rise from sort of points in some P-divisible group, or we're ordinary at the prime P, which is kind of a technical condition. But this is stronger than just being potentially semi-stable at P. And of course, we're going to require our determinant to look like the determinant of a modular form. So it's some character times an integral power of the cyclotomic character. And what we'd like is to be able to stop at that point and just say that the representation is modular. Unfortunately, we can't. And what the theorem also needs to have is that the residual representation is, well, still irreducible, and even irreducible, say, when restricted to the Galois group of Q bar over the Q adjoin the square root of plus or minus P, where this is the quadratic field inside the pth roots of unity. And furthermore, that this residual representation is nice, so you have to impose some conditions on its restrictions to the primes where it ramifies. So these are local conditions. And finally, we have to impose sort of the mod P modularity conjecture. So we have to require that rho bar be modular. But given this, and since I haven't told you what nice is, you might believe it, the conclusion is that the representation is, in fact, the representation associated to some modular form. And this is enough to prove, for instance, that all semi-stable elliptic curves are modular, and so finally yielded the proof of Fermat's last theorem. And what I'm going to do for the rest of the talk is to discuss some of the ingredients that went into this proof, because I want to be able to discuss some of the refinements or generalizations that have occurred in the last few years, and I need to be able to refer to these ingredients. So the idea, by now familiar to people that have said in talks like the one I'm giving, is to identify deformation rings and Hecke rings. So I need to say a few words about what these are. So let's talk first about deformations. So this is going to be completely unrelated to automorphic forms. This is something in the world of Galois representations, or group representations more generally. Is if we fix our ring O, this chaotic integer ring, such that our representation that we're interested in takes values in GL2 of O, then we'll formulate a deformation problem. And we'll talk about deformations of its residual representation. And what they'll consist of is some complete local Noetherian O algebra with the same residue field as O. So this is some nice category of rings. And we'll, together with, say, a representation into GL2 of this ring A, this algebra, such that if we reduce this representation mod the maximal ideal of the algebra, we get back the residual representation. So somehow we're looking at all kind of lifts of our residual representation, and then we can formulate deformation problems. So we can look at classes of deformations with prescribed conditions. So we can say, well, let's look at just all the deformations with ramification in some finite set of places, and then maybe we can pose further restrictions at these primes. And then if for certain nice deformation problems, there's sort of a universal solution. What this means is that there's some deformation with these conditions. So here, denoted by rho sub d and the corresponding algebra or ring R sub d. And this is universal with the following universal property. Given any deformation of type D, so having these conditions D, there exists a map from RD, in fact, a unique map from RD into the algebra A, such that the obvious composition gives you at least a representation that's equivalent to the one you started off with. So these are the deformation rings that you want to connect up with something in the world of automorphic forms. And that something is a Hecke ring. So what one tries to do then is to construct a ring T sub D, where D is the deformation problem, which is a Hecke ring generated, say, by O, which we now sort of view as living inside the complexes, if you like. And Hecke operators acting where? Well, only, we're going to say, restrict to that space of cusp forms spanned by the eigenforms which give rise to deformations of the type that we're looking at. And since we're hoping that all of our deformations come from these modular forms, this is kind of the right space to look. And at least under the hypothesis that the residual representation is irreducible, you get a deformation of the type that we're interested in into GL2 of this Hecke ring, T sub D. And the important point is that this is such that the trace of a Frobenius element is the Hecke operator T sub L. So here's the connection between the two things. The universality then, since we have this deformation of type D into TD, gives us a map from RD into TD, into this Hecke ring, which turns out to be surjective. The trace, the Frobenius, is now going to map to the Hecke operator T sub L, at least for for primes away from those in our set sigma where we're allowing ramification. And then the conjecture would be that this map is an isomorphism, so that this Hecke ring really is the universal object. I should say that these sorts of ideas were floating around in Mazur's original paper on deformations of Galois representations, and at least in the case of ordinary representations, I think it was even formulated in a paper by Mazur and Tel Aviv, and then of course made very precise in Weil's paper. The consequence of this is, of course, that if we have our representation into GL2 of O, and if it's of type D, then if we have this isomorphism, the representation is modular. And just check what that means. Well, the identification of RD and TD gives us a map from TD to O, which sends the Hecke operator to the trace of the Frobenius in our representation rho. On the other hand, given any such algebra, or any map from the Hecke ring, we know there's a modular form such that the Fourier coefficient or the Hecke eigenvalue at L is the image of TL under that. So what we're saying is that there's some F such that the eigenvalue at L is the same as the trace of Frobenius in the representation, and that means the representations are the same. So say a few words about the strategy of the proof. So this is my rip-off of the cartoon by Sidney Harris. So I'm going to break it down into two steps, or three steps actually, and sandwich between the first and the third, which seem kind of understandable to me as this sort of mysterious second step, which is really still a miracle. So the first step is you formulate the correct deformation problem, sort of a minimal deformation problem where you impose all the possible restrictions that you can. And then you need to prove, so we'll call this T sub 0, and then you need to prove that the Hecke ring actually exists. So you need to know that there are modular, sort of these minimal modular deformations, and here's where you invoke this theorem of Ribbit. So we're starting off with the hypothesis that we have some modular deformation, and we need this really minimal one. This is the one that sort of Sayre would conjecture exists, essentially. And then, in our miracle, we sort of managed to prove that we have an isomorphism in this minimal case. And I'm going to skip over that for the moment and and move on to step 3, which is, now that we have this isomorphism, show that that's enough to conclude that we have an isomorphism for less restrictive deformation problems. And here, what happens is that there's a numerical invariant, well, attached to each of the rings RD and TD, such that if you have equality of these numerical invariants, then you have, in fact, not only an isomorphism of rings, but an isomorphism of complete intersections. And it turns out what this miracle produced was not just an isomorphism, but an isomorphism of complete intersections. So you have this equality at the minimal level, and then you just need to figure out how these numerical invariants are changing. And the numerical invariant attached to the deformation ring is just controlled by a Galois cohomology group. So you just need to compute some orders of Galois cohomology groups, no problem, right? And the second numerical invariant, that attached to the Hecke algebra, is somehow measuring congruences of modular forms. And so you need to measure sort of congruences between new forms and old forms. And this can be done by refining some methods of Ribbit and Diamond and others. So you can get good control over how these things change, and in fact prove that you have equality of these numerical invariants. So that's the strategy of the argument, at least if you buy step 2. And so for the rest of this talk, I want to talk about various generalizations, simplifications, and applications. So one great application, of course, we've already seen, the modularity of various classes of elliptic curves and Fermat's last theorem. But so this theorem, of course, opened up an entire new area, and well, whenever that happens, mathematicians rush in. So there have been quite a few results in the last few years. The first, following quickly on Weil's theorem, was a result by Fred Diamond, which removed many of these conditions on rho bar being, the residual representation being nice. It removed a lot of these local conditions on the residual representation. And so one theorem that you might get is that, well, suppose rho is as in the previous theorem, so it's continuous, irreducible, unramified, outside of finely many places, etc. But now one only needs to suppose further that rho is still, rho bar, at least the residual representation, is irreducible when restricted to this quadratic extension of Q. It's still modular, but we can get rid of a lot of these local conditions and say flat or ordinary, and well, this is a technical thing, dp distinguished, meaning that you can distinguish certain characters in the ordinary representation. I'm probably missing something there, but the spirit, that's the spirit of the theorem. And then the conclusion, of course, is exactly what we want, that the representation is modular. And this was enough to conclude that elliptic curves that are semi-stable at 3 and 5, the primes 3 and 5, are modular. And of course, being that much closer to the full modularity of all elliptic curves, people started working very hard on this, and there are a couple of papers, the first by Conrad, Diamond, and Taylor, which weakened the restrictions at P, so you allow sort of you allow just sort of one of these potential semi-stable conditions, so that maybe you become flat or ordinary over a finite extension. And they were able to prove, using that elliptic curves that become modular over a tamely ramified extension, or become semi-stable over a tamely ramified extension at 3 are modular. And then they finally completed the full proof of modularity of elliptic curves using results of Breuil on classifying semi-stable representations. And then there have also been technical refinements of the proof. And independently, Diamond and Fujiwara introduced a technical refinement in this sort of mysterious step 2 that removed a lot of the hard algebraic geometry that went into it. There was this condition about being Gorenstein or having multiplicity 1 geometrically. And that was originally used in the proof, and now that becomes, not only is that not needed in the proof, it becomes a consequence almost of the proof, or of this method of Diamond and Fujiwara. And then there's kind of this really neat sequence of arguments that's come out recently due to Ramakrishna and Kare, who are trying to avoid that mysterious step altogether. And what it does is it goes back to this idea of Rabi of just producing some characteristic zero lift of the representation. And maybe you can squeeze your deformation problem enough that not only is there a characteristic zero lift, but there's only one. So you can really pin down what that universal deformation ring is. And that's done by forcing ramification at lots of primes. And then, this is just the idea of what goes on. So you require ramification, some auxiliary set of primes Q, and that forces the deformation ring to actually be isomorphic to O itself. Now, on the other hand, we're assuming that you're modular. So you've got a modular deformation, and you have to now show that you've got a modular deformation that's ramified at these primes Q. And so that requires studying some congruences. And if you did, then you would get an isomorphism R dq is isomorphic to T dq, because there's just no room to have any difference between them. And then what you want to do is go from that to deducing that you have the isomorphism for a general deformation problem, at least for deformation problems that are large enough. And so there's a preprint out that sort of carries this out for certain classes of deformations. Unfortunately, for example, it doesn't apply at p equals 3. So it still wouldn't say anything at all about elliptic curves. So those are sort of the results over Q. This technical simplification that I alluded to of Diamond and Fujiwara sort of makes it possible to obtain some results now with Q replaced by a totally real field. And so Fujiwara has worked very hard on this and has a number of preprints claiming to have proved R equals TD. So sort of a result of the deformation ring is isomorphic to a Hecke ring in many cases. And as you might imagine, there's a number of technical hypotheses that intervene, not the least of which is some version of Ribot's theorem, this sort of minimal modular lift. And also working over totally real fields, Wiles and I obtained a few years back some results for residually reducible representations. So up until now, all the results have been requiring that this residual representation rho bar be irreducible. And so it's sort of natural to ask, well, what happens when it's reducible? And this would occur, for instance, if your elliptic curve had a p torsion point and you were looking at the p-adic Tate module. And in this direction, we proved a number of theorems, and maybe the cleanest is the following. Suppose p is an odd prime, so we're still shying away from p equals 2. And suppose we have one of these Galois representations that we like, unramified away from finely many primes, etc. And suppose we're ordinary, so that's this condition that when we restrict to a place V dividing P, that we're one of these upper triangular representations. Really, this is sort of nearly ordinary, and you would require that this character have finite order on an inertia group. And then we have to impose a couple conditions on the residual representation rho bar. First of all, it's semi-simple and reducible, so it's a sum of two characters, chi1 and chi2. And we just want the characters that occur in our restriction to deformation to be ordered naturally as given there. So the bar denotes reduction of the character, and they should be distinct. That's a not equal sign. So this is the notion of being dp distinguished. And then for technical reasons, just because we don't understand enough about class groups, we make the hypothesis that if you look at the splitting field of the quotient of these two characters over F, this is an abelian extension of Q. So in particular, F had to be an abelian extension of Q. Then we can conclude that the representation is modular. And so in some sense, we've sort of gotten around Serre's conjecture. Nowhere did we assume that the residual representation is modular. On the other hand, it's sort of modular for free. It's kind of the reduction of an Eisenstein series. So now that I brought up this epsilon conjecture for totally real fields, I should mention that the techniques that we used to prove this theorem, we could also use to prove results where the Galois representation is residually irreducible, and here F is still a totally real field, and we're ordinary at all places dividing P, and we have to assume residually modular, that the residual representation is the reduction of some Hilbert modular form. But we don't have to assume minimally ramified at all places in this modular lift, that we can make use of results of base change, in particular knowledge of the image of base change, to avoid that, and by making congruences with various other modular forms. So a few other applications. Everything so far has been for p odd. So what about p equals 2? So the only results that I know to this date are in the thesis of Mark Dickinson, who graduated a year or two ago from Harvard, who worked on some cases of representations that are ordinary, so some two-adic Galois representations that are ordinary at 2, and was able to establish modularity. And Fujiwara also has some results as well, although it's not clear to me exactly what he's claiming. And using his results at p equals 2, one can obtain some new examples of cases of the Artin's conjecture. And Artin's conjecture, well, Artin has many conjectures. So this is the Artin's conjecture for automorphic forms people. This is the I started out in Diophantine equations. There's another Artin's conjecture in Diophantine equations. This is the conjecture that if I give you a finite dimensional complex representation of a Galois group, that the Artin L function is analytic if you don't have any copies of the trivial representation sitting inside there. And so, together with Kevin Buzzard, Mark Dickinson, Shepard, Barron, and Taylor, there are a number of new cases. And I didn't have the paper with me when I was preparing the slide to figure out exactly what the statement of their result is. But, and I should say, there are also some other examples being worked on by Idre Goins, who's here at the conference. So finally, I find myself on my last slide because I ran out of slides last night. What about other groups? So everything has been for two-dimensional representations now. So we can go back to, but what about sort of three-dimensional representations or four-dimensional representations or, so on? Let me find one slide here. So what do we need to actually get a result in these cases? Well, certainly we're going to need Galois representations attached to automorphic forms. And hopefully we'll hear more about this on other groups. In other talks and other groups this conference. And what do we need about these representations? So we probably need something like the restriction of these representations to the Weil-Delim group is what you would expect from the local Langlands correspondence. It may be possible to get away with knowing this only for principal series representations, which is surely easier than in general. So we would still have to try to figure out which representations come from automorphic forms in the first place. So for example, what kind of conditions should we oppose at P? Well, there's a potentially semi-stable condition, but how do we really realize that? What's a notion of minimal lifts? Do they exist? Is there an analog of the Serre's conjecture? Can you prove the epsilon version of that? Certainly, these conjectures exist and are out there. And, that Gross has a good candidate for them. And then to make all of this work, we're going to have to be able to compute congruences between automorphic forms on higher groups of higher rank. And congruences, I mean congruences between systems of Hecke eigenvalues. And here it becomes sort of very complicated, at least combinatorically. And there's been some progress, say, for GLN with n bigger than 3. Fairly recently, there's a student of Richard Taylor, Russman, who's done some work there. And then I understand there's a recent paper of Clauzel on Ribot's sort of level-raising theorem for GL3. Unfortunately, our library doesn't have that volume of American Math Journal yet, so I don't know what exactly the statement is. But I would guess that any and all of these are still very much open problems. And since that's my last slide, I'm going to stop there.
So are there any questions? There's plenty of time. Yeah.
There's a question. What's in the kernels of the kernels. I mean, what are they fixing? Well, so what you have is up after a finite extension. So you make some finite extension, and what their images are pro-p groups. So their images are pro-p groups unramified away from finally many places. So they're whatever the quotients are they give you, essentially they give you that. Except they're even more special than that, because they're the ones that sort of take images in these p-adic Lie groups. But other than that, I don't think anyone really knows what the kernels look like. Ah, okay, so right. So I alluded to p equals 3 at some point. And so we had this condition that rho bar must be residually modular. There has to be a modular form that lifts it. And so this is a version of Serre's conjecture. And really the only case that we know is when, say, that p is 3 and our image is in GL2 F3, so that and we have solvable image. So we can embed this into GL2C, essentially, and we can invoke Langland's result on Artin's conjecture for the strong Artin's conjecture for such representations, that there is a modular form giving that representation. So that's why p equals 3 is important. Well, the strong Artin conjecture for n greater than 2 might be a start. For example, there's a recent work of Dinakar Ramakrishnan on for some higher dimensional things. I think in GO4, so general orthogonal group of 4 dimensions. Sorry. Well, oh, the odd condition. So odd condition, of course, is that the eigenvalues of complex conjugation are 1 and minus 1. This is what you expect from a representation attached on GL2 to something with a discrete holomorphic series. For GLN, what do you expect? Well, the expert's actually sitting over there talking to somebody else. Presumably, it'd be something like it contributes to the cohomology, although I imagine that that's too weak, that there will be cases where you have Galois representations that don't contribute to cohomology. Well, we know that already, actually, for GL2, where you've got Galois representations for holomorphic things that are weight 1, but the infinite component doesn't contribute to cohomology. But certainly, contributing to cohomology would be a start.
Well, if there aren't any more questions, let's thank the speaker again.